Hello everyone, I'm Norman Wildberger and thanks for joining me. I'm going to give you some more advice today along the same direction as my last video where we were talking about extending number theory by thinking more broadly in terms of polynumbers, not just regular numbers. And I sort of stressed to you that factorization in some sense is more interesting and more insightful really in the bigger polynumber world. So factorization of ordinary numbers, as we mentioned last time, is it's unpredictable, but it's also a little bit tedious. Every number has a factorization, and it's almost random, how the factorizations go. And if you know the factorization of a big number, you still don't really know very much. However, the story with polynumbers is much richer. And factorization there is a very interesting phenomena. So when you have a polynumber or a polynomial which actually factors, then it's telling you something important about the underlying mathematics. Now, I have to point out in a very strong way that this is a counter to the usual story that you're taught in undergraduate mathematics, which is all about the fundamental theorem of algebra, telling us that polynomials basically always factor. Well, let me tell you very clearly, they do not always factor. And there's a common statement, for example, that polynomials with, say, rational coefficients or over the real numbers factor into linear and quadratic factors. This is just absolutely plain wrong. Approximately, yes. Okay, but as an exact statement, it's wrong. And it's really important for you to get on board with that thinking. And it's, in fact, sort of demonstrably wrong. You just write down any polynomial of reasonable degree, even something relatively simple like x to the 7 minus x plus 3. Try to factor that into linear and quadratic factors and see how far you go. Okay, so the point of view that I'm trying to explain to you is that factorization is actually an indicator of structure, and it's an indicator of interest. Okay, and so this is really important, especially when we're looking at these families of polynumbers that I was telling you about in my last video, which are, playing really important roles in lots of areas in mathematics, physics, chemistry, etc. So today we're going to have a look at the arguably the most important family of polynumbers. Now, if you ask a regular mathematician, a pure mathematician, what are the most important families of polynomials, they'll probably say the Chebyshev polynomials of either the first or second kind. But we're going to see that the spread polynumbers, which are variants of the Chebyshev polynomials, are pretty clearly more important than the Chebyshev polynomials. And I want to indicate that to you. That should be a flag of just how big and exciting a new area we have here, because these spread polynomials are so interesting, not just from a geometrical point of view where they're crucially important, but also in terms of analysis and in terms of number theory. And the highlight will be a remarkable factorization found by my honor student, Suxian Go, some years ago, the Go factorization. So let me start with the Chebyshev polynomials. It's a very big subject, and I'm going to ultimately make a whole series on spread polynumbers, and the Chebyshev polynomials will figure prominently. So I will at some point elaborate on these. So very quickly, okay, the simplest way of introducing the Chebyshev polynomials is through a recurrence relation. Okay, so there are t sub n of x. So n is an index, natural number starting with 0. And t0 of x is defined to be 1. t1 of x is defined to be x. Those are the initial conditions. And then the recurrence, which drives them, is t sub n of x equals 2 times x times t sub n minus 1 of x minus tn minus 2 of x. Okay, so we use this recurrence to successively create more and more of these Chebyshev polynomials of the first kind. And pretty clearly, Tn of x is going to be a polynomial of degree x, because each time we're bumping up the degree by 1. Okay, so what do these things look like? Well, they're polynomials that can be graphed, and it turns out that their values between -1 and 1 are particularly important. Okay, because they bounce around from a lower value of -1 in that interval to an upper bound of +1 in that interval. And they do so very beautifully. So they start, so for example, t sub 4 is this light blue one here, okay? So it starts up here at -1, 1, and comes down, touches -1, goes up, tangent to +1, goes down, touches -1, and comes back up right up here. So they all do this. Of course, outside this interval, they go up, typically, towards positive infinity or negative infinity, depending on their degrees and so on. Okay, so what actual values are we talking about here? Well, it turns out that there is an interesting generating function, which is sort of a remarkable way of sort of capturing all of them. Okay, it's just given by this little, maybe I'll just highlight this. It's just a great little formula. The generating function is, let's display it, t of x comma t, which is 1 minus tx over 1 minus 2tx plus t squared. So what is this? Well, this is like a ratio of polynumbers, but there are two variables floating around. The x, which is going to be the x that we're using to describe the Chebyshev polynomials, and a further variable called t. So if you look at this as a function of t, it's a rational function. Okay, so you have a linear polynomial in t in the numerator and a quadratic one in the denominator. So basically it's a division, right? This formula is in some sense asking you to do a division. And if you do a division, well, you can do that in the context of power series or Pauli series. Okay, you're going to get a series in t, but each of the coefficients of that series is going to be a polynomial in x. And happily, all of the Chebyshev polynomials get marched along one by one as coefficients of the various powers of t in the expansion here. So if I get my computer to just expand this as a power series in t, I get this expansion here, 1 plus tx plus t squared 2x squared minus 1. That's telling me that the second Chebyshev polynomial is 2x squared minus 1. And then t cubed times 4x cubed minus 3x. That's the third Chebyshev polynomial, and so on. Okay, and of course it carries on. So it's a little bit more easily visible here in this matrix, or this column. Okay, so we see all of the Chebyshev polynomials from t0 up here to, I guess, t sub 10 down here. Now, by the way, the reason I'm writing it this way, usually I like to write polynomials or polynumbers starting from the lower degree terms, but my computer just automatically outputs this, and it's too much work for me to reverse the order. So just keep that in mind. Okay, so what do these things mean? Well, one sort of standard interpretation of this is that it's a way of relating cosines with cosines of multiples. Okay, so for example, you may know that cosine of 2x, okay, equals, well, one way is to write it as cosine squared x minus sine squared x. Perhaps you've seen that. Okay, let me just see if my computer recognizes that as a true statement. Okay, yes, that's true. Now there's another way of writing that, because we can replace the sine squared with a 1 minus cos squared. So we could get rid of the sine squared and just express it in terms of cosine. And we get 2 cos squared x minus 1. Yeah, that's an alternate expression for cos 2x in terms of powers or polynomial just in cosine x. Okay, and that's where this second Chebyshev polynomial is coming from. It's one explanation for it. So the third one, which will be less familiar to you, cosine 3x. So the claim here that you can see by reading off the third polynomial is that this is 4 cosine cubed x minus 3 cosine x. Let's see if my computer believes that. Yes, that's true too. Now, whenever we talk about such transcendental objects, we should clarify what we're talking about. So in most modern analysis courses, the interpretation of such a statement, like I've just written down, is in terms of functions. Okay, that cosine 3x is a function that inputs x and outputs cosine 3x. And this right-hand side is also a function, and these functions agree in the sense that if you plug in a real number x and compute it, then you get the same thing on the left and right-hand sides. That's not, as in capital N-O-T, the way I want you to think about the meaning of this statement. Okay, the meaning of the statement is much better. The meaning is much better understood in terms of Pauli series or power series. And let me indicate what I mean by that. Okay, so let's take cosine 3x and let me get my computer to write out a Pauli series for it, or a power series, okay, in x now, because it's in x. Okay, so there it is in x up to degree 10. And now let's take the right-hand side, which is another power series ultimately in x, and we can compute it, or my computer can compute it. I will do the same thing in x, please. Thank you. And we see that these terms are the same, at least up to degree 10. So the meaning of this statement, as far as I'm concerned, okay, is that we have an equality of power series. That's, or Pauli series better. So there's a power series or Pauli series on the left. There's a power series or Pauli series on the right. And these are equal. And what does it mean to be equal? It means that their coefficients are equal 1 by 1 as we increase powers, in this case of x. It does not mean that they are equal as functions, because there's no way of evaluating these things as functions. As functions, this is an infinite task that we're not able to do, and we can't pretend that we can evaluate such a thing. But what we can do is we can successively march through these things, okay, and notice that we have equality of coefficients, and then aspire to proving that the general coefficient of x to the n for the first one is equal to the general coefficient of x to the n of the second one. So I'm making a big deal of this because it's really important that you start thinking this way. It's crucial for the Algebraic Calculus 2 course, which I hope some of you are taking, okay? And it's just a better way of thinking about what's going on with analysis. That's just the way it is. Also fits much better with the way physicists think. Okay, so those are the Chebyshev polynomials of the first kind. Okay, a little bit more quickly now. The Chebyshev polynomials of the second kind are very similar. They also satisfy a recurrence relation with u0 of x being 1, u1 of x equals 2x, and actually exactly the same recurrence relation for higher degree terms. So the only difference between the first kind and the second kind, Chebyshev polynomials, is the u1. With t's, we had just x here. Now we have 2x. And here are some graphs of some of the first ones. u0, u1 is just a line. u2 is the quadratic one. Where is it? Here in green, etc. Okay. And what about the actual values? Well, there's actually a generating function too. The generating function is actually even a little bit simpler. It's just 1 over 1 minus 2tx plus t squared. And you can just spew that out and write down these various values. So these are particular values for the Chebyshev polynomials of the second kind. Now, before we get to the spread polynomials, which is really the main interest here, I want to have a look at the question of factorization. So suppose I take one of these things, okay? Say this is the Chebyshev polynomial of the first kind. Something that you should routinely do when you see some of these polynomials is ask, do they factor? Okay, as I mentioned at the beginning, that's a kind of a crucial question. So let's actually see if our computer can factor that. Okay, it factors it, but not in a very spectacular way. Well, let's have a look at this one here, the degree 8 one. How does that factor, if at all? Now, we can't expect such a simple factorization. And it doesn't factor. Okay. How about number 9? that factors in a kind of an interesting way. That's x times 4x squared minus 3, which is a little bit like this thing here. This thing here has such a factor also, I guess. And then there's this other term, which is 36x squared. Okay, it's not in order. Minus 3 plus 36x squared minus 96x to the 4th plus 64x to the 6th. So some factorization is going on here. Occurs here. And people have studied this. But it is, let's say, not so obvious what the pattern is. Let's just say that at this point, okay? Now let's look at the Chebyshev polynomials of the second kind, okay? And oh, by the way, I should show you something cool. So I can do all of this factorization at once. Since I have all of these things in a matrix, my program will allow me, if I just put factor, to factor all of them at the same time. Isn't that nice? So we see that there's some sort of non-trivial factorization for this one. I guess that was degree 6, and degree 9, and also degree 10. Okay, there's some number theory going on here, right? This is the algebraic equivalent of factoring numbers. And yes, it's also a little bit random, but maybe not that random. Maybe we can understand the factorization. Let's have a look at the Chebyshev polynomials of the second kind. Here they are. Let's factor them all at once. Okay, we get something over here. Oh my goodness, look at this. See, this is a much richer factorization. And there's some, interest here. There's some factors which are reappearing, at least a little bit, although there's new ones too. I guess these ones here are more or less like these ones. Yes. Have we seen this one before? I don't think so. Okay, there's something to be investigated here with these Chebyshev polynomials of the second kind. So the factorization seems a little bit more pleasant. The factorizations here appear to be, let's say, richer. But we're not really sure about that. Okay, the spread polynumbers or polynomials were introduced in my book on rational trigonometry about 15 or 17 years ago, and they are very closely connected with the Chebyshev polynomials, as we'll see, but offer important advantages, especially from a number theoretical point of view. So what I'm trying to do here is, I'm not going to go into details about these things, but I want to get you thinking about broad new directions. And the spread polynumbers are just a perfect example of so many opportunities that we have of discovering interesting new things, which are really available to amateur mathematicians. And I do intend to do an Explorer research level mathematics series on spread polynumbers, so you can think of this as a gentle introduction to that. Okay, they are defined by a recurrence relation, very similar to the Chebyshev polynomials. S0 of s equals 0, S1 of s equals s, and then this recurrence, which is a little bit different because there's a plus 2s at the end, okay? Otherwise, it's 2, 1 minus 2s times Sn minus 1 minus Sn minus 2 plus 2s. Here are some of the first values of the spread polynumbers. Particularly interesting is the second one. That's worth noting. So note that S sub 2 of s equals this thing here, which also factors maybe it's better to write it like this. Sometimes called the logistic map. Okay, and there's further values. So how do we get at these things other than having to run their recurrence? Well, there is a generating function, just as the Chebyshev polynomials have. This was found by Mike Hirschhorn, who's a colleague of mine at UNSW and an expert in all kinds of interesting analytic formulas and combinatorics. And he discovered that the generating function is say, this function of s and variable t. T is the same w variable that was appearing in the generating functions for the Chebyshev polynomials. So it's t times s times 1 plus t over 1 minus t times 1 minus 2t plus t squared plus 4ts. So a little bit more complicated, okay, a little bit more complicated, but you could still use this to generate some of these things. Now, the connections with the Chebyshev polynomials are really important to mention. So this one here is prominently the most important one. It's telling us that the spread polynomials are intimately, are really just an affine shift of the Chebyshev polynomials. And maybe we can sort of illustrate that here with this little diagram here. Okay, that's maybe a bit too far up. So here's the relation, okay? It's saying that Sn of s equals 1 minus Tn of 1 minus 2s over 2. And what that really effectively is doing is it's taking the Chebyshev polynomials and sort of compressing them. So instead of going from the interesting range -1 to 1, if we look at that box plot that I showed you before, x going from -1 to 1, y, or yeah, y going from -1 to 1, and sort of translating that, shrinking it by a factor of half, and then translating it over, then it occupies a box going from, say, x or s in this case, from 0 to 1 on the horizontal axis, and also from 0 to 1 in the vertical axis. Okay, so we're going from -1, 1 cross -1, 1 to 0, 1 cross 0, 1. And that's the effect of this essential affine shift here that I showed you. That's relating the values. And here are, well, a graph of the first 16 spread polynomials or polynumbers. So there's s equals 0, that would just be the axis here. S equals s, so that's that line that's going up there. And then you can see this parabola here, right? It's doing the same kind of thing that the Chebyshev polynomials do. They start, down here, and they end either down here or up here. And they bounce around up and down in this box, tangent always to the bottom and the top of the box. And you can see that there's all kinds of interesting things sort of happening here. There's sort of concurrences, and maybe you can even, if you stare at it in the right way, you can maybe also see some sort of ghost curves. Again, can you see a parabola sort of in that general shape there that's sort of visible as a gap somehow formed by the graphs? So pretty interesting. Well, what else do we know about them? There's also a connection with Chebyshev polynomials of the second kind, given by this formula. And might also mention, this is sort of an interesting fact, that if n is odd, then Sn of s has a factor of s, and then the rest of it is always a square. While if n is even, it has a factor s and another factor 1 minus s, and then the rest is also a square. That's pretty interesting. But there's lots of other things to say, but the most remarkable thing that I know about them is this fact. This is a conjecture which I'm going to, okay, we're going to call this Go factorization. Okay, so this is named after Suxiang Go, who was an honor student with me at UNSW some 15, 17 years ago, and he wrote a very nice honors thesis on the spread polynomials. And he noticed this very elegant fact, that the spread polynomials factor in a very nice way. So here's the exact statement. For every k, a natural number, 1, 2, 3, there is a polynumber phi sub k with integer coefficients, and it happens to be of degree phi of k, where that's the Euler totient function, sometimes called, which counts the number of numbers which are less than a given number and relatively prime to it. Okay, so there are these polynumbers phi sub k, and then for any n equals 1, 2, 3, a natural number also, the nth spread polynumber, okay, is a product of phi sub k's. A product of which ones? Well, all the phi sub k's for k a divisor of n. It's exactly a beautiful factorization. So this is now a list of these phi sub k's, we might call them Go polynumbers, that occur in these factorizations. So there's now a secondary family of polynumbers which are acting as, in some sense, sort of like, primes. It's sort of like a prime factorization, isn't it? But we're not factoring into numbers, we're factoring into sort of simpler polynumbers. And these are almost all squares. That sort of follows from the thing I just told you, except for the first two. Okay, but all the other ones are squares. And they are quite unpredictable, I think it's safe to say, okay? And in my course on spread polynomials, we're going to have a very close look at this. And there's just, so much investigation, a really rich number theoretical investigation that emerges from studying this. So let me illustrate this factorization, okay? So for example, S12. 12 has factors or divisors 1, 2, 3, 4, 6, and 12. And so there's a factor of S12, one for each one of these Go polynumbers of the associated kind. So phi sub 1, phi sub 2, phi sub 3, phi sub 4, phi sub 6, phi sub 12. Okay, phi sub 1 was just a S. Phi sub 2 will be this one here. Okay, phi sub 3 is also appearing. See it there. Phi sub 4, it's also appearing. Phi sub 5, no. But phi sub 6 is also appearing. There it is. And phi sub 12, which is not on this list, turns out to be, I suppose, this thing here. And there's a couple of factors of 4 merging from here and here to give us the 16. So this is quite remarkable. And let me illustrate that by going up to our list of polynumbers, okay? And I'm going to factor this so you can sort of see this in action. Factor. So here are the factorizations of this. And if you compare these factorizations with the Chebyshev polynomial factorizations, you will see that these are much, much nicer, okay? Exactly because of this formula that was found by Xiang, that the factors that are appearing here are in some sense very predictable, and they only depend on the divisors of the number n that you're considering. And these polynomials that are associated with divisors are fixed. They do not depend on the n. It's the same factors all the time. Okay, so this 4s minus 3 squared, that's coming from here. Okay, that's like the phi sub 3. That will be occurring in all of these places where we have something divisible by 3. Okay, so it's an absolutely beautiful thing. But of course, it then opens up this question, okay, how do we understand these phi functions? Okay, and that's a very rich question, and I want to encourage you to think about this as being the number theory of the future. Okay, this is like a really rich direction for number theory to go, and it's almost a wide open direction. Okay, so much for amateurs who are interested in either algebra or analysis, polynomials, special functions, number theory to investigate.